Good morning to you all. What we are going to learn today is about pipeline architectures. So let me first explain you what a pipelining is through a simple example. For example, let's take a case of a laundry, okay, where an n number of people put their clothes and expect it to be washed, dried, and folded and pressed. Okay. Now these are three different activities. Okay, first one is the clothes needs to be washed. So you will have a washing tub, and then a dryer where the clothes after washing it will be dried, and then you manually there will be a person employed who would fold it and press it. Now suppose the time taken for each of these activities is 30 minutes, 40 minutes, 30 minutes for just for washing, 40 minutes for drying it, and 20 minutes is for folding and pressing it. Now suppose he has got a lot of clothes from 4 different customers. Excuse me. 4 different customers. Okay. So you have so the amount of time which he is going to take to complete this task is so each of this, for each customer he is going to take 30 minutes for washing, or 40 minutes for drying, and 20 minutes for folding and pressing, right? Then so the total is going to be 1.5 hours. So another 1.5 hours for customer B, 1.5 hours for customer C, and 1.5 hours for the customer D. So you have a set of 4 customers. So the total time is going to be taken required for this completion of this task would be 1.5 into 4, so it would take 6 hours. So if you start somewhere at 6 p.m. You are going to finish it somewhere in the midnight. And now if you see here, what is a pipelining concept? Now each of these 3 activities they are independent. So you have an independent washing machine, right? You have an independent dryer, and you have a person employed for folding and ironing it, right? So can we have these things running in parallel? Yes, it is possible, right? So see once we start at 6 p.m. Washing, at the end of the washing 30 minutes, you will find this washing machine is now free. So instead of waiting for the entire cycle to get completed, I can put the clothes of the customer B at 30 minutes, right? And then at the end of next 40 minutes, I can put that customer B, even the dryer gets free by then. So I can put the clothes of the customer B into the dryer, right? And end of another 40 minutes, you will find even the person who is employed out here, he is also free here. So he can be also be employed again for that. So if you see here, now things are running parallelly. Okay, but at any given time you will find here, if you see here in the first slot out here, okay, the washing machine is employed only for one of the activities. Out here also the dryer and the washing machine is used. Here the person, the dryer and the washing machine both are used. So there is no overlap, right? So there is no issues with this. Okay, it is only since this particular activity has been split into 3 different activities, and most importantly the resources required for each of these activities are different. The resource required for this particular act, now this is a complete single activity, they have been split into 3 different activities, and the resources which has been allotted is different for all of them. Now here you have a washing machine with a separate power supply, okay, so it can run independently. Okay, it is not that you are plugging this there in that particular socket. The resources have to be different, independent, so that they can run independently, not depend on each other. So when this is running, it's not dependent on these two, right? Whether the clothes is being washed here or it is being folded here, it doesn't matter, because you are drying it here. So as long as these 3 activities are not dependent on each other, you can run them parallelly like this. Okay, so if you see here, if you do this kind of overlapping, then the total time taken is just 3.5 hours, compared to the 6 hours which we initially saw here. Here it required 6. Okay, this is a sequential work, whereas here it is a pipeline work. If you see here, so you see here a lot of time has been saved. So if you talk in terms of a processor, your processor speed has increased. Now you can expand this analogy to your processor also. So this is what a pipelining structure is, right? So the same thing. Now if you have an instruction to be executed in a microprocessor, it can be first of all, the instruction needs to be split. Okay, here the instruction has been till now we have been and if you see here, whatever we have learned till now, where the processor architecture was divided into two: an execution unit and a control unit. Okay, in the control unit, what we were doing, the instruction which was fetched was being decoded, and that was happening parallelly. At the same time, in the execution unit, the ALU was there, and there were some shift registers and certain activities of computation of the next address, or doing add and operations and all logical operations that was being done in the execution unit out here. So this is for a microprocessor, I can assume that the total instruction can be divided into two: fetch and execute, and there are two different units available, independent units available to do these functions. Okay, you have an execution unit and you have a decode unit. So each of these instructions can be split into fetch and execute cycles. Okay, so this is our known as. So the first instruction has been divided into two: fetch cycle, execute cycle, fetch cycle, execute. And this is F3 for the third instruction, and an execute cycle, right? And what is important out here is you need a buffer out here. Okay, now what is the requirement of a buffer, right? Because first of all, the first requirement is these two should be independent hardwares, right? You can't have the same hardware doing these two instructions. So you have an execution unit which is different, and you have an instruction decode unit which is different. Okay, so that part is taken care of. Now why do I require an instruction, right? See the first instruction has come. We have fetched that instruction and we have decoded it. So now we are giving that input to the execution unit. While the execution unit is executing it or implementing that particular function which is being given here, right? The instruction fetch unit is trying to compute the next instruction, right? So if this data is going to change out here, the results of the execution unit is going to get corrupted, right? So whatever instruction was given earlier for a particular cycle, that needs to remain constant till the execution unit completes the task, right? Parallelly, the instruction unit is also working. This is also working, but at the initial, when the cycle has initiated, whatever the instruction unit has given, that data needs to be kept constant for the execution unit to complete that task. So that is the reason you have a buffer. Buffer should be a register which will hold the data till the next cycle. So in the first cycle, from the instruction fetch, you have some data which is captured here, right? Now the execution unit, depending on that data which is available in the buffer, will do the task. And in the end of the cycle, from the execution unit, the result will be available, and in the end of the cycle, once this execution unit completes the task, the next instruction will be put into the buffer, right? And since we have the data available in the buffer, instruction unit, because that data is captured here and it is available here, now the instruction unit can parallelly function. So these two are the important conditions which are mandatory for implementing pipeline concept. So here, if you see here, it is written fetch, execute, and when this is being executed, the second instruction is being fetched and decoded, and it is being executed here. Then you have, when this is being executed, you have the third instruction being fetched, and that is being executed out here. So this is known as pipelining concept, with the instruction being divided into two steps, right? So but then if you see here, if you divide this into several into instead of 2, if you make it into 4 different steps, the pipelining will become more effective, right? So you will find your throughput increases, right? In the very first class we discussed what is throughput. Okay, so you can use a higher clock, because each of these instructions now has been now here if you see here, initially if I take this whole thing, if it takes around 10 nanoseconds, now if I split into 2, each of these will take in only 5 nanoseconds. So my clock can be of 5 nanoseconds. Okay, now instead of this time period, now instead of this instruction, if I and then I have 2 instructions being run parallelly. Now instead of that, if I divide this instruction I1 into 1 2 3 4, I2 also into 1 2 3 4, then each of those blocks might take only 2.5 nanosecond. I'm just giving rough values. So 2.5 nanoseconds. Now so the clock speed also increases. Now you can use a clock with 1 by 2.5 nanoseconds frequency, right? So your clock frequency has gone up, and what happens, you are more efficiently using the hardware which is available, because now there will be 4 activities running in parallel by dividing this into 4. That is the reason here if you see here for a pipeline instruction, okay, it is actually 4 steps. Okay, one is known as fetch. Okay, the other one is decode. Fetch is reading the instruction from the memory. Decode is decoding it so that the exact control signals is made available to the execute. Execute is the ALU operation, and then the final is the write operation. So writing either to the memory, or the result of the this will be returned to a register. So both options will be there in the write operation. So these are pipelined into 4. Now and like we discussed earlier, here also, since we have divided into 4 different, so we need to insert an buffers at each of the states, right? So because if you see here, in one cycle output of the execute is available here. Now it is being written to the register or to the memory, while the execution unit is performing the next action. But till this completes this action, you can't change the data out here, because again what is being written will get corrupted, right? Similarly, here also what you have fetched data, it is being decoded. So while this is fetching the next instruction, this needs to be kept in a constant, right? So you have one more buffer. This we again discussed in the last slide, that while the execution is being done, you need to keep these control signals constant out here. So these are known as interstage buffers. Okay, buffers, in fact I would like to call it as interstage registers. Okay, because they are not pure buffers, but they are registers, okay, which are clocked. Okay, so as long only based on clock, till the next clock comes, the data will be held as it is in these registers. So these are all registers which are inserted in between these hardwares. Okay, this is a single cycle for completion of an instruction, but they have been divided into 4 sub blocks, and we have inserted registers in between. Okay, so this is known as a pipeline concept. Now if you see here, now the same instruction has been divided into 4. You have an fetch instruction, you have a decode instruction, you have an execute, and then you have a write to the memory or to the register, right? So this is one instruction which is happening. So now parallelly in the pipelining structure, once this instruction is fetched and decoding is happening out here, then you can fetch the second instruction without waiting for this entire cycle to get complete. In the third clock cycle, this decoded data will start getting executed. Meanwhile, this fetched data will start getting decoded, and now the third instruction will be fetched out here, right? And then you have here, and the fourth cycle, the fourth data being fetched out here. So if you see here, 1 2 3 4 5 6, in the end of 7th cycle, we have all the 4 instructions been completed, right? If you don't have a pipeline structure, 4 into 4, it would take 16 clock cycles, right? Here if you see here now, right, for this to happen again, let me reiterate. These are the two things. The hardware needs to be separate, right? Only then the fetch part and the execute part, hardware needs to be separate, and there has to be a buffer in between. Okay, if those two conditions are met, then we can implement it like this, which is known as the pipelining concept. Okay. And now if you remember in one of the initial classes when we discussed, we learnt about CISC and the RISC type of computers, and we mentioned that RISC computers are better for pipelining. Okay, and now why I said that then is, if you see here in this in the complex the instruction set computers, you have different types of execution commands, right? Each you can have complex execution commands which can take more than one clock cycles. You could have a simple command which will take just one clock cycle, or you could have a complex command which can take 3 to 4 clock cycles in the CISC register and the computers, right? So if you see here, now what happens, the second it's taking the time taken for this execution is 3 clock cycles out here. So now the third instruction, I cannot load it, right? Because now if you see here at the end of the clock cycle, this is not completed the task. Here there was no problem, they were all completing in one clock cycle. So sequentially I could put in one about, and I could finish it in 7 clock cycles. But here if you see here, so this requires more than one clock cycle. It requires 3 clock cycle. So these needs to wait out here. Now you will have a spiraling effect. Even the next instruction cannot be pushed out here, because this is F4, because D3 is not this decode block is not clear out here, because D3 is held here, right? So you'll have to wait in between for this execution cycle to complete, and then so these kind of interruptions in the pipelining is known as stalling. Okay, the stalling of the pipelining. Okay, and this occurs because the execution cycle is not constant for certain instructions. For complex computers, okay, CISC computers, the execution, the instructions are such that they require a varying amount of clock cycles to complete the execution. Okay, so that is the reason. So stalling happens there, right? Okay. Now, if you see a simple processor, if I see the block diagram, this is known as the fetch. Okay, here you have instruction memory, okay, into which from the program counter, okay, it tells how to decode the instruction, right? So if you see here, what is the input coming to the program counter? Here if you see here, it is through an adder. So every time the PC is incremented and a new PC is being given here. Now this adder, okay, is actually the same as that of an ALU, right? Now, but then you might say, okay, initially, sir, you said that the hardware of each of these blocks should be different, whereas this adder is actually part of the ALU, right? Then why have we shown it as different? Okay, the reason why it is, although it appears that this adder is part of the ALU, but since we are using multiple phase clocks, okay, so within this this period there will be 4 phase clocks, and in one of the phase clocks we will be using the same ALU out here. Okay, so that is the reason you have this adder. This is not an separate adder. Okay, the ALU itself it is actually part of the ALU, so it is not a separate hardware. It is only a time shared. Okay, although it is physically the hardware is the same, but virtually they are used at different period of time by using multi-phase, and that is the reason this adder is placed out here. Also is shown out here also. So you have an address coming, instruction and a fetch. Okay, the new instruction, the memory is being fetched out here. That is known as instruction memory. It is either coming from PC or it is coming from some other place also. It's coming from here. Okay. What is this? If you see here, Okay, it is coming from the instruction itself, right? So sometimes in the instruction you have those are jump commands and unconditional jumps and conditional jumps, right? In those cases, you are not increasing the PC, but the new address is being fetched. So that is the reason you have an alternate path which is available out here, right? This is instruction decode. So whatever is the instruction, this we saw the hardware, right? Again, the instruction decoder, based on the instruction, it will generate the control signals for the ALU. So what are the inputs available for this here? If you see here, now the registers are also a part of this here, right? So this is not an execution unit. Okay, now don't think this entire thing as control unit and execution unit. Okay, they are classified into 4 groups based on the task. Okay, so some registers of the execution unit are also grouped out here. Okay, the control word decoder of the control unit as well as the registers of the execution unit are put together here in the instruction decode and register file read. So if you see the name of this particular block is instruction, it's not only instruction decode but register file. So all those registers which we initially saw in the execution unit, they are also placed out here. Okay, now what we said the instruction is coming here. From the instruction, one set of data will go to the ALU, right? Now also it will tell the ALU what action it needs to be taken, and also the second set of data also will go through here through the multiplexer. Okay, now why have we used a multiplexer out here? If you see here, sometimes direct data will be available for into the ALU, right, for immediate kind of commands, right? So sometimes, right, and also from the memory also, right? It could be one input for an ALU has to be a register. Okay, what about the second input? It could be a direct data or it could be a memory data. So there could be 2 different types of data which is going to the ALU. One has to be a register. Okay, so that is the condition which is there. The second could be either an immediate data or an immediate data will be available in the instruction. Like for example, RX plus 5. So that plus 5 is just an hexadecimal number plus 5, right? So that will be available here. Or it could be from the multiplex from the memory also. So you have a memory here and you have that memory coming here, right? So from the memory also through the write data registers. So that is the reason. So this block, now you have an ALU which will do the necessary computation, and the output is available to the write memory write block. Now the output of this, from this memory block, either it goes into the memory or you can write it back to the register also. So that is why you are using an mux. So sometimes from the ALU the data is returned into the memory, or for register to register operation you don't have to write the data back to the memory, right? In that case, the output of the ALU through this mux, it is returned back into the register. Okay, so output of the ALU can go into 2 places. One, it can go to the memory. Okay, in that case this write data signal also will be given, so that this memory reads the data from the ALU. Or in other cases, the output of the ALU through this mux, is again returned back into one of the registers. So now we have split this particular hardware into 1, 2, 3, 4 blocks and a mux finally to route the output. Now we need to insert buffers in each of these stages, right? So because that we already saw, when the instruction is being decoded, you have to keep is being fetched, you have to keep that instruction constant for this to decode it. So this register will be known as instruction fetch stroke ID register, right? Instruction decode. From again you have one more set of registers. Okay, it is a 32-bit register, right? So you have instruction decode stroke execution unit register, and then you have execution output of the execution register being fed to the memory. So instruction execution unit stroke memory register, and you have memory register stroke write back. Okay, write back is suppose this data requires to be returned back into one of the registers, then we have this register. So each of these registers will hold the data in a particular cycle. It will be initialized during the on a first edge of the clock, and it will hold it till these registers, okay, till each of them will complete the task. Okay. Now if you see here, I'm not complicating here, but remember that each of these may be multi phase clock. So in T1 phase, say all these registers will be updated, right? And then you will have a multi phases like T2, T3, T4, which we learnt in our previous classes, wherein these things they will work. So the ALU might do the computation in T1 clock. It might do this in T3 clock or T2 clock. So all those things will happen. So this essentially in the T1 clock, this data will be captured, and till the arrival of the next T1, this data will be held as it is. Okay, so this is known as this is how these registers are required to be inserted in between each of these stages for implementing an pipelined processor. Right. Now if you see here, each pipeline stage is expected to complete in one clock cycle. The clock period should be long enough for the slowest pipeline to complete. Right. Here we assume that F1, D1, E1 and everything is taking one clock cycle, say 10 nanosecond. Suppose the fetch is taking 20 nanosecond, whereas these are taking 10, 10, 10. Then actually my clock has to cater for the slowest block, the fetch instruction, right? So it has to cater for the slowest block, it says, right? Now what happens is many a times the time taken to bring the data from the memory, okay, is large. Okay, so that then the fetch instruction becomes, and similarly to write a data into the memory also, it will take a large time. So fetching the data from the memory, whereas a decode and execution especially for a RISC processors, they will just take a very less time. Whereas getting the data from the memory and writing the data to the memory might take a long time, and they will determine the clock speed, okay, since they are the smallest block. So that is the reason we use something known as cache memory. Okay, what is a cache memory does? Since the main memory is slow, okay, so the part of the memory which we are interested in, from that memory, the data which we are interested in, that will be brought into a cache memory, which operates very fast and which is placed close to the CPU, so that the instruction fetch and the data write operations become faster. Okay, so let me explain you that. So this is the secondary storage, and it could be our hardware, right? And like a hard disk or and the hard disk which we place, right? From there, so the program which is being run, okay, so that particular program will be loaded into the not the entire storage, right? The storage could be 1 TB, 2 DB, right? And then the data which is required, okay, the programs which we are running, that will be brought into the main memory. Like main memory is nothing but the RAMs which we have. These days we have dynamic RAMs, right? So you have 1 GB RAM, 2 GB, 8 GB, 16 GB, up to 16 GB. This could be in terabytes, right? So from here, the programs which we are running, so that will be, those programs will be brought out here, right? So this is only around 16 GB, right? I think even 32 GB is available, but generally 8 GB to 16 GB is the ones which we are generally using in our laptops and computers, right? So some it speeds up, right? So you don't have to keep fetching the data from the secondary storage, which is the hard disk. Now even to make it further faster, you can have a cache memory, which could be just this is a dynamic RAM, and these are known as, so dynamic RAM is again it is a high density RAM, so you can go up to 8 GB, 16 GB. SRAM, you don't have that much packing density, but they consume more power, and but they are very fast. So you could have a smaller cache memory also. It could be just 1 GB or something like that, or even lesser than that, but that can be kept very close to the processor itself. So generally the communication has to be between the cache and the processor. Okay, so this will constantly, as the program changes, constantly these cache memory and the main memory data, as you are moving from one program to other, or within the program as you keep moving from as the program counter increases, so these cache memory and the main memory data will keep getting updated, so that normally there will be a lot of exchange between the processor and the cache. Okay, so it will be much faster. So that brings down the instruction fetch and data write instructions. Okay, if that time comes, then your overall processor speed improves. Okay, so this is the this known as cache memory. Now if you see here in modern processors, if you have an CPU within the chip itself, you will have a small cache memory, right? And then you could have this is known as L1 cache. You could have one more cache, SRAM cache on the motherboard, and then you could have a DDR RAM. Okay, so if you see here, and then you will have a hard disk. So from the hard disk, data will be brought to DDR RAM, and from the DRAM to cache L2 cache, and then from there to L1 cache. So this is how the CPU ensures that the least amount of time is wasted in trying to fetch the instruction. So the relevant information will always be kept in one of the cache memories. Okay, so this is how cache memories help in bringing down the instruction fetch and write time, and they will prevent a stalling of the pipeline structure, right? So you will find here in this block here, you have an data cache and you have an instruction cache. Okay, so some instructions which are being referred now constantly, that is kept in the instruction cache. Similarly, some data which is being continuously accessed. Okay, so that is kept here. So many a times you will find that the same instruction is being, so you could bypass the ALU also. If some data is already available in the data cache, a result of some operation, when you are calling for that operation, you can bypass the ALU and you can take that data from the cache memory and give it to the output. Similarly, if the same instruction is being called again, so you will find that that instruction is available already in the cache memory, so you can take that instruction from the cache memory instead of from the main memory. Okay, so these kind of cache memories help in speeding up the overall microprocessor functions. Okay, now if you see the pipeline performance, as you keep increasing the pipelining stages, okay, the performance improves. But if you have to keep increasing the timing, you have to ensure that even the small blocks, okay, they are able to do it within that time. Now because the big time you are splitting into small times, so that puts a stress on each of these blocks. So they have to finish the time within this given time. Okay, but that doesn't happen. Okay, so now the same example which we saw earlier, if you see here the execution is taking more time, because so this is, so you will find that here and here there is an stall which is happening. Okay, so whenever any instruction, okay, not only execution, it could be in the fetch cycle also. It can happen in the fetch cycle also with complex addressing. So we'll see those examples also. Here I am talking about say the addition. Okay, in addition, it will take 1 clock cycle, but multiplication is going to take more than 1 clock cycle, right? So, and that is the reason when we talk about a RISC processor, we just had an instruction of add, right? So the multiplication will be taken care of by the software algorithm there, not in the hardware, right? So whereas in the complex instruction sets, even the multiplication needs to be taken care of. So you will find addition and multiplication both are being done, or division, so they will all take different amount of clock. So RISC computers are, that's why is more suitable for pipelining instructions. Okay, Now whenever a pipeline gets stalled, okay, for 2 clock cycles, okay, we call it as an hazard. Okay, so whenever whenever like this is a hazard, this is known as stalling, right? Stalling means stopping for the previous instruction to get completed. Okay, although this has completed out here, now it has to wait for the execution unit to become free. So this is known as stalling. So whenever stalling happens, we call it an hazard, right? So there are 3 types of hazards which are there. One is known as data hazard, one is known as instruction hazard, and then there is a structural hazard. So a data hazard, any condition in which the source or destination operands of an instruction are not available, okay, at the time expected. Okay, so that is known as data hazard. We'll see some examples so it will become clear. Instruction is when the instruction is not available, and structural hazard is when the same hardware is required by 2 different instructions. In that case, we call it a structural hazard. So we'll see each of them separately. Okay, certain instructions. Like what is a data hazard? Certain instructions like multiplication, division require more than 1 clock cycle here. Like so now this is known as a pure data hazard. So because it is this data is not available out here at the end of 1 clock cycle, right, into the W. Okay, so this data from the execution unit is not available after 1 clock cycle to the right register. So that is why there is a stall out here, right? So this is known as data hazard. So we can take few more examples. Okay, now suppose you have an 2 instructions. Okay, this is one instruction, this is one instruction, which are running in one after the other. Here we are telling A is 3 plus A. So now A register A needs to be updated with data A plus 3, and then the next instruction we are telling B needs to be updated with A into 4, right? So now if you see here, there is a hazard which is going to be there here, because after the execution of this unit, in the next cycle only this data will be returned into the A register, right? So meanwhile I cannot push B data here. If I go back to this here, right, let me take a simple block where there is no hazard here. Right, now I am here, suppose in this instruction here let me take here A plus 3, right? I am doing A plus 3 here, and I'll be writing A plus 3 in the next cycle to the into the A register. Here I am just doing A plus 3, and the data is temporarily available in the ALU register only. It is not written into the A. It is written into the A into the next cycle only, because I have divided this instruction cycle into 4 different parts. So this is the write operation. Now meanwhile I am doing B plus A. Now if I do B plus out A here, right, this is going to write here. So here I am going to take this data, okay, of A. This is A is not yet updated here. A will be updated only end of this cycle. So here execution unit I cannot write. If I write here, it will take the previous value of the A, not A plus 3. Whatever was there previous here, because the write will happen only at the end of this cycle. Only A will be updated here. So this is known as again data errors which can happen. So if I go back here, right, so these kind of instructions can cause data hazard. Like whereas this instruction is, if you see here, A is 5 into C. In the next instruction is 20 into C. Here the C data is not being updated. C is constant. So you can have a pipelining out here without any hazard. This can cause hazard. This cannot cause hazard. Okay. When 2 operations depend on each other, they must be executed sequentially in the correct order. It says, right. So otherwise they could be an order. So this is again shown here out here. Now one more example is shown here of data hazard, where you have a register R1. You are adding R2 and R3, contents of R2 and R3, and putting it in R1. So here in the ALU, okay, you are adding R1 and R2 out here, right? The data is available here in this, and then you are writing it in here addition is completed here, and here the data is being updated. Now if the next instruction is an R1, R5, R4, right, here this is the ALU, right. Now what at this particular time, this register R1 is not updated, R1 is updated here, so there is a data hazard here. Even in the next instruction also, here in the AND also, if you see here, this register data will be captured out here, right. So here also R1 is not updated. Here it is okay. Now this register is updated here, from here it is going. So here, so in these two cycles, in these two instructions, since R1 gets updated only at this particular point of time, so here you will find a previous value of R1 will be used out here. Okay, R1 is being updated here in the first instruction, right, and in these two instructions, the updated value of R1 will be used. In these two, the previous value of the R1 will be used. So that is known as a data hazard. So these kind of situations should be avoided. Now how can we avoid such situations is by having a temporary register in ALU. Okay, so we saw that a T1 register was being used in the ALU when we saw the hardware, and now the result of the T1 was further used later on to write from the T1 to one of those registers, and it was left up to us when to update the T1, right. So if you see in the previous classes, we learnt about a T1 register which used to hold the data of the ALU. So if you have a temporary register here, right, okay, that can be used again in the ALU out here, right, by giving an feed. It is known as data forwarding path. Okay, so the result is now going to the right register. At the same time, that data is available in the T1 register for the ALU. If required, the ALU can use that particular data out here, right. So what happens here? This data available from that ALU is also available in a temporary register, and that can be used here. Okay, that can be used here, not this register. So that from T1 it can be used here. Similarly, from T1 it can be used here. So we can get rid of these data hazards by using another temporary register, and that is the reason when we studied the microprocessors, the output of the ALU, we had one T1 register, temporary register, where the output of the T1 was available. Okay, that was available on not always, but whenever we wanted to store the data of the ALU, you could put from ALU directly to the address out buffers also, but we through a control switch, if you remember, we were able to put the data of the ALU into an temporary register also. So that is known as operand and forwarding of the forwarding path. So this is available. So this alternate path ensures that we gives us a means to overcome the data hazard. Okay. So also you could have like suppose you have a multiplication R2, R3, R4. Okay. So the multiplication itself will run a small program, right. It requires a few cycles, right. So what happens is immediately we don't write an add operation in a RISC operation. So we can write some NOP. Okay, NOP means no operation, right. So if you write these kind of commands in between, it helps this cycle to get completed. So NOP will not do anything, but it will just insert some time gap for this multiplication. So multiplication takes much more time than the addition. So you have an NOP, okay, no operation commands written in between. So you can do this in the software also to avoid the data hardware. So while writing a program, you can cater for additional times, okay, for like NOP to enable this instruction to get completed. So depending on the number of cycles which is required for multiplication, and those many NOPs can be if it's a division, or I'm just giving one example, but depending on if there is an instruction which requires more than one clock cycle, okay, one machine one clock cycle, then we can one microcycle I should say, then you will you can put those many number of NOPs in between. So that is one option of one method of handling the data hazards. Okay, so Now similarly you could have an instruction hazard also, right? Like generally it happens if you miss an cache. Okay, now what is missing an cache? Now if I see here, if I go back to the cache memory, yeah. So not necessarily when I am running a program that the particular data or the instruction will be in the cache memory. Many a times it will happen that if there is some instruction when you are encountering it, the next instruction may not be available in a cache. In that case, you will have to revert back to the main memory and or maybe the secondary storage also to get that instruction, right? So this is dynamically updated, but many a times it may not happen. This has to, some algorithm has to run and prefetch the instructions and put it into the cache memory so that there is a smooth flow of instructions from the cache to processor. But your algorithm cannot be 100% full proof, where the required next instructions will be brought and kept earlier itself in the cache, right? It can happen. There could be some similarly it may not be available in the main memory. So there might be cases where that instruction is not available in the cache, and then the processor has to go to the main memory and get. So you will find here, okay, so where is it? Data hazard. Yeah, you might have to wait for the fetch instruction. So you will find there is a stall which is happening out here. So this is known as, so you will find here, okay, these have to be, the next instructions have to remain idle. Okay, so especially for unconditional branches, right? It could be a far jump also, right? So suppose you are doing an instruction and then certain particular for after doing that particular instruction, unconditional jump is you just jump, it says okay, next jump to such and such memory location. Now the program has to start from that. So that particular bunch of instructions from that new location needs to be fetched from the main memory to the RAM and to the cache memory. So it will take time. So these kind of stalling can happen whenever we are encountering unconditional branches also, right? So that is known as it is known as missing of cache memory, right? So what is the way to get over that? One is instruction queuing, right? So if you have learnt in 8086 microprocessors, you might have seen that there are 6 registers available as instruction queue. That means the instruction 6, like while I am executing say instruction 1, the instruction 2, 3, 4, 5, 6, 7, 8 is fetched and kept in the queue and decoding is happening, right? So you have an instruction queue registers, a set of registers. It could be 6, 8, 10 and depending on your requirement, where the instructions are prefetched and placed in the queue, okay, so that if there is some extra time required, that can be catered for. So that this is known as instruction queue. So it is not that when I am doing the instruction, the very next instruction is being fetched. Okay, you are going to fetch the instruction 6 or 7 instructions ahead itself, and you are going to push them into the instruction queue. Okay, so that will give us then some kind of buffer time available, so that a smooth pipelining can happen, right? So this is known as instruction queue, and each of them will be decoded. So this is known as instruction queue. So this is one way of doing it. The other way is branch prediction, right? So this we saw in our earlier class also, when we were talking about hardware maps. So if you see here a 0 flag, if it has to jump, if the condition is met to 0, okay, where the program has to jump to a location specified by the RY register, right? So if the probability of jump is very high, okay, what we do is here these blocks are left empty here, showing that there is some execution being happening here. Okay, so this is level 1 flowchart actually. So here some execution is happening. Parallelly, what I am doing is, since the probability of RY is very high, I am going to place this contents of RY into the address out buffer, and also I am incrementing, I am also placing it to the ALU, so that after this the next will be ry plus 1, right? So that also I am doing out here. And if z is equal to 1, z is equal to 1 means this condition has been met, a 0 flag has gotten flagged. Okay, now you will find, since I have already prefetched it, so I am going to put it into the execution register, and then from T1, the T1 is what? Now it will have ry plus 1 that is being updated into the PC. So you will find that you have predicted the branch out here, and without wasting time, so the pipelining doesn't get stalled out here, right? So in case there is no branch, then I will have one more additional cycle will be required out here, because now again from the PC the data needs to be put to AO and then increase, and then the instruction needs to be fetched here, right? So this is the block. So in case the probability of z being not being 0 is high, that means z is not being 0 is not being flagged. In that case, we write the program separately out here, where we are loading the AO with the normal PC count, and in case 0 is encountered, then you update it here, right? So it all depends. So the probability of stalling out here in this particular case, okay, will be lesser, because here you are expecting that in most of the cases it will not be 0 out here, right? For example, if you have set a counter like C, so when the counter reaches 0, you will jump out, okay? But normally for say if the count is 64, for 64 clock cycles you don't expect a counter to be 0. So this is how now we can implement those kind of functions and prevent stalling in the fetching of the data, right? So you could have something known as a dynamic branch prediction also. Okay, so what is it? This is like, if you see, branch likely to be taken and branch is not likely to be taken. So here you have to initially itself decide, right, whether it is branching is happening or not. Here dynamically we are deciding either to implement this or to implement this. Okay, which scheme needs to be implemented, that is being decided through a branch prediction logic. So if it is here branch is likely to be taken, and again if the branch is taken, it will continue to remain in this state. If the branch is not taken, then it will go to this state. Okay, a branch not taken. Okay, so if it is branch not taken, then we'll implement this particular scheme, and if branch is to be taken, this will be implemented. So that decision will be taken by a dynamic branch prediction out here. So this is, you can implement it like this, or you could have a 4-state machine also. Here if you see here, this is branch likely to be taken in this state, and again if the branch is taken, okay, a branch likely to be taken, it's already in branch likely to be taken. Again one more branch is taken, then it will come to this state, which is branch strongly to be taken out here, right? Again if a branch is taken, it will remain in strongly to be taken. If its branch is not taken, then it will come back likely to be taken. Again if it is not taken, it will come to strongly not taken, because you have two branch not taken simultaneously coming in, so you have strongly not taken, right? So if it is again not taken, again it will remain in strongly not taken. But if a branch is taken, then it will go to likely not taken, because you have one branch not taken, and then you have one branch taken out here. So that is why you downgrade it to branch from strongly to likely not taken, right? But again if you have a branch not taken, you go to strongly, or if it is taken, you come back to strongly taken, right? So two strong branch takens will get it into strongly taken. Similarly two branch not taken will get it into strongly not taken. So you could have a dynamic prediction branch also implemented like this. Okay, so now coming to address modes, right? So you in a complex instruction sets, you have an indexed addressing, indirect addressing, auto incrementing, auto decrementing. So all of these will take different times. So and hence, okay, addressing modes, when you have complex addressing modes, they affect the pipelining. Okay, so that is why if you remember in the RISC processor, we have a simple addressing modes where we can just load the data into the register. We can't have an ALU is supplied with only register to register operation in a RISC processor, whereas in a complex instruction registers you can have register direct, register indirect, all those kind of things. Okay, so they all result in hazards or side effects. Okay, so we'll see some examples. So it will become now for example out here. Okay, load R1 and R2. Here no address computation is required. Okay, it will be done in a single. So whatever is the memory location, okay, in the address out buffer we place the contents of R1. Okay, this is the memory location specified by R1 register. So that memory location address will be placed in the AO bar, and from the data bus that data will be written into R2. Okay, now if you have an instruction, okay, R1 plus displacement is given in R2. Now what I have to do, now the memory address needs to be computed, right? So the displacement X, okay, which is given in the instruction itself, and the contents of R1 needs to be added to generate the address out here, and then it is, so you will find here, okay, two clock cycles are required here. One additional data is required here, right? So you will find here D2, D1, E2, one more instruction is required out here, okay, to compute the memory address. So there is a stalling which is going to happen out here, right? So these kind of addressings will create stalling. Okay, in CISC computer you can have even more complex instructions, right? You can have like this. What is this? The contents of R1, okay, will be fetched from will be added to a displacement X, okay, and that data, okay, that memory location, the data from that memory location will be fetched. Okay, that actually is again one more bracket is here, that actually corresponds to an memory location again. So you will find, okay, first you add X plus R1, okay, and then you fetch the data from that memory location. Okay, now this is not data actually, this is memory again, because you have put one more, you are adding contents of R1 with X. Okay, now one memory location has been computed. Now from that memory location you are getting this data, okay, and that data is actually now is at memory address. Now you require one more, so you will see the number of clock cycles has increased. So here if you see here, so this is now you find there is a stalling out here which is happening because it requires many operations. So these complex addressing modes they create issues in pipelining. So these are not suitable for complex addressings are not suitable for pipeline instruction. The address modes in modern processors only from the load and store instructions. The RISC processors, they use just the load and store. From the memory it just comes to the register, from the register it goes to the ALU, and from the ALU again it comes back to the register, from the register it can be stored into the memory. So that is why the RISC processors, if you remember the MIPS MIPS instruction sets, we had only a simple load and store instructions, if you remember from one of our previous classes. Okay, so now coming to the last kind of hazards, which is known as structural hazards. Okay, now if you see here, you are loading the data from the memory. This is register ALU. In the last cycle you are writing the data into the memory, right? So right from into your memory location, and here also you are fetching the data from the memory, right? So you will find the same memory is being accessed here and here also, right? So this is known as the structural hazard, where the memory is being the same hardware is being used by two different instructions at the same time, right? So this could be an issue. These are known as structural hazards. Okay, but this is also again overcome by using multiple phase signals, because instruction fetch will be completed in the first phase clock, whereas this write operation will happen in the last phase of the clock. So if you remember the previous class where we discussed about the timing signals, here, okay, although the same hardware is used here and here, but then still we can overcome this issue by using multi-phase clocks. Okay, so this is known as this is again showing here the memory is being used in the same thing. Here it is shown in the horizontal time scale where it is being used out here, right? So this can be overcome by using multi-phase clocks. Okay, so with that we will call it off for today.